focus of our session today. We're going to talk about STL creation, which is the front end of 3D printing. So we develop a CAD file. We're going to create an STL file from that CAD file. We're going to import it into a 3D printer, and we're going to output it into a part. We're also going to have one of our partners, Farrell, talk about the use of reverse engineering, which is taking a part, scanning it, creating a CAD file to either re-engineer the file or output it into a 3D printer. So we're going to speak on behalf of Farrell and that technology, which is very exciting. Trimax Solutions is an engineering resource company. We're headquartered in Richmond, Virginia. We've been in business about 21 years. We serve the commercial, government, and DoD design and manufacturing industry. Okay, so any company that makes chairs right through to nuclear aircraft carriers. So a wide range of things that are being designed and manufactured. We are a long-time 20-year SolidWorks CAD partner in both sales, training, and service. And we serve those clients in the commercial government design space with SolidWorks. We are pretty much embedded throughout the southeast, eastern United States, from Pennsylvania to Florida, and west to Mississippi and up into Arkansas, using Virginia as the sort of western border. So a lot of states, a lot of regional offices. We have a wide variety of engineering resources that we provide our clients. Not only SolidWorks tools, but also the training and design functions of SolidWorks, but we have an in-house engineering team that can provide assistance to our clients with design, simulation, and all those type of things. We also have a recruiting and staffing arm of our business that helps our clients find mechanical designers, electrical engineers, put them in seats, whether it be long-term, short-term contract assistance. We're a government services contractor. We team with large defense contractors to bid on government contracts with both these SolidWorks tools and human resources, whether they have mechanical engineers, electrical engineers, designers, drafters, to fill those contract needs. We are a 13-year Stratasys partner as well. So embedded in the Mid-Atlantic. My role as the Additive Manufacturing Territory Manager is to meet with manufacturers of all shapes and sizes, of all kinds of things, to help them assess their current processes and how they design and manufacture parts, and how additive manufacturing could be used or supplemented to their current processes. Okay, so part of the wonderful piece of my job is that I get to go see some really cool things, and I get to meet a lot of manufacturers, whether it be government or commercial, that make a lot of interesting things. I'm a former soldier, so I get to work with DoD. That's very exciting to me. We also work with Walter Reed, NIST. NIH is a huge Trimax client for 3D printers and SolidWorks, so I get to see and meet a lot of interesting people. Okay, so to wrap up, what I do, I'm going to try to impart just I'm a salesman. Okay, so I'm going to try to hide that, but I'll try to impart to you my experience in the field from the percentage that I've been told, but I've seen more than 80% of the manufacturers that could use a 3D printer in their business do not. So there's still this gigantic piece of the manufacturing industry that's not using additive manufacturing. And the general feeling that I get when I meet with that segment is a confusion. And what I try to do is to try to simplify their understanding the best I can. So 50% of what I do is missionary work, trying to help people understand and diffuse the myth and try to focus it in closer, because there's so many choices, there's so many obstacles involved and so many considerations. And some. But I try to break it down and simplify things. So for companies that are out there that are looking at 3D printing or the first 3D printer, I'm not sure, they may have a small understanding of what they're going to do with it, and they're scared of the price and how we're going to get that back, quickly to justify this purchase of one of these machines. Try to break it down into 4 buckets for them, okay, of the potential use of a 3D printer. One would be concept and design. We're just going to draw the part, and we're going to 3D print it quickly and put it up on the desk to see if we even, if it even makes sense from just a concept and design standpoint, okay. The second piece would be prototyping or functional prototyping. We're going to print those parts out, we're going to bolt them together in assembly, we're going to do fit checks, we're going to do those kind of things. We're past concept and design now, we're going to do actual physical testing and those kind of things from a prototyping standpoint. The third bucket would be jigs, fixtures, and tooling, as mentioned out there in the first session. Assembly aids, drill guides, fixtures, those type of things that aid in the assembly or the manufacturing of the product, okay? And then the fourth bucket would be end-use parts. And that's the holy grail of 3D printing, okay? Where we're going to take the part out of the printer, and we're going to bolt it right into our product, and off it's going to go in space. Okay, that's where everybody wants to be. And it's a small segment. It is happening, and it's all driven by materials and the requirements of the part and what it has to do, because you have to stand up to. So when you're looking at 3D printing, what are you trying to accomplish with the part? What are you trying to do with it? And then when you determine what you're going to do with it, what materials will stand up to what you're going to do with it? And then which machine prints those materials to determine if it's going to stand up or not. Okay, so I try to break it down into simple parts first. And from an ROI standpoint, justifying concept and design is very difficult to get back that ROI from that bucket. Okay. Jigs, fixtures, tools, tooling, those kind of things that we do manufacture, that's where the fastest ROI comes back on a 3D printer. Because traditionally that stuff is made from metal and requires a programmer and a CNC operator and all the things that come with traditional cutting from steel. Okay, 50% of that stuff may be able to be made from a high-performance plastic. So it may not last 100 years, but it may last 5 years, and if it does, it snaps and breaks it from another. Okay, so that's, a lot of companies aren't seeing that. I need a one-off tool today. I only have 2 weeks, 3 weeks to wait for my machine shop to put me in the queue for a month from now. I've got to have that today to fix a problem or an obstacle. We can have it designed, send it to the printer, we can have it the next morning, and we can get it out there on the manufacturing floor. So the compression time is its #1 value statement. So those are just some things that I see in the field is this reluctance to, there's just so much information. Why does your machine cost so much when I see one that's for $500? Well, we got to understand what is it print, how is it going to perform, whether it's mechanical properties and those kind of things. There is no silver bullet printer. There are many choices, and each one of these machines caters to a particular application better than the other, or not at all. So, consumer-grade printers have their space. The commercial industrial printers have their space. The media is creating some confusion as to the crossover. Consumer-grade printers are catering to the education market. And companies that are trying to make their step into additive manufacturing are purchasing the consumer-grade printers to prove concept. It's a low-risk proposition. We can teach our people how to create their system and their process with this. And then once we validate that, we show the people upstairs that we have saved time. That furthers going out to purchase maybe a commercial or industrial printer that can then start putting out some high-performance parts. So there's a process. So that's what we do at TriMet, wide standpoint with CAD tools. So I'm going to hand it off to Chris Weedergreen now, who's our SolidWorks representative for Eastern Pennsylvania, and he's going to lead us into the actual STL creation portion. If you have any questions for me, I'd be happy to answer. Maybe not from a Stratasys-centric standpoint, but just from understanding how we can potentially use this or bring bring it to our company. So I'd like to say thank you and enjoy the rest of your conference.
Thank you, Steve. So I want to thank everyone for coming here. I didn't expect this many people, but I'm glad to see this many people. We will be taking questions. We have roughly 20 minutes per segment, so I'm going to take a couple minutes and I'm going to introduce the first speaker. One of the things that we do at TriMech is we like to highlight our clients. So both Andrew and Michael are clients of ours and utilize this technology in various ways. So what better way to say, how do I create an STL file, than to have people that actually do it. So without further ado, I'll start my bit. All right, where do we start? I always like to have a couple quotes because I think it really sets the mood. Imagination is the beginning of creation. You've imagined what you desire. You will what you imagine, and at last, you create what you will. So part of what we do as engineers and designers is we think, what do we want to do? How do I want to get this thought into actual my hands? Two ways to do that. You machine it, or you can 3D print it. And like we heard from the first session, the air intakes for the F-22 Raptors, you can't machine that. You can't do a double helix inside a double helix, but you can 3D print it. So that's one way we get our imagination into our hands. Ken Robinson. You could be creative in anything, in math, science, and engineering, and philosophy, as much as you can in music, or in painting, or in dance. So again, creativity in our design. And you have to have that model, right? How do you get that model? You're drafting and scanning. All right, without further ado, this is where the actual creation of that idea becomes in reality in the STL. Michael Creighton is an engineering manager at Creative Mechanisms, and they are about an hour and a half south in Warminster. And they are clients of ours, and they utilize the SolidWorks technology and the Fortis 3D printing. So, Michael.
Can everyone hear me okay if I don't have the microphone? So like Chris said, I am Michael Creighton, the engineering manager at Creative Mechanisms. We are a contract design engineering prototyping firm just outside of Philadelphia. We mainly focus on injection molded parts, but also, as our name says, things that have complex mechanisms somebody else can't figure out. They bring it to us. We help them figure that out. We offer a few unique services. The first is you have one-on-one contact with the engineers, like myself, or we have 6 other engineers in our office. If you have a project, you're actually talking with that engineer one-on-one as opposed to going through a salesperson or something else. And then we have a few proprietary processes that we have, specifically CNC machined polypropylene living hinges. It's not really additive manufacturing, but it's another niche market we have, something that we're doing no one else is doing. I have some samples out on the TriMech table if you'd like to take a look at those. So what are we going to talk about? We're talking about STL files here, how to create them, what they are, where you get them from, what you do with them. We'll go through a couple walkthroughs at the end of this presentation just to take you through the entire process. If we look up here in the middle of the screen, that is our company logo, the Creative Mechanisms logo, saved as an STL file. We would take that STL file and 3D print it on our 3D printer, which is the Fortis 400 machine made by Stratasys. That's what we have in our shop. We print with ABS material. We bought the machine about 10 years ago. It's still state-of-the-art. You can't buy that specific one anymore, but we were kind of an early adopter of that machine, and we've been using it ever since, very happy with it. So what is an STL file? So STL comes from, find some space here. STL comes from stereolithography. This was covered a little bit earlier. You can see the ST and the L. You might have also heard this as SLA. Developed by 3D Systems, it uses a laser to cure photopolymer in that vat of liquid. It's kind of like the first mainly adopted 3D printing process back in the 80s and 90s. But you take that STL file that they created for that process and you use it in all these other 3D printing processes too, like SLS, FDM, DMLS, PolyJet. They all use the STL file. It was an industry standard. You still use it today. And because it was an industry standard, you find a lot of people that were in the industry back in the 80s and 90s, they refer to all 3D printed parts as SLAs, even if they're being printed with FDM process or PolyJet, whatever the material is. So you got to be careful. You'll hear someone say, is that an SLA? They're just saying, is that a 3D printed part? Okay, so what is it? Little cut off there, but it's an approximation of your 3D CAD data. And it's approximated using triangles. So it's a bunch of triangular facets. It takes all of your CAD data and approximates it. If you have curves, it puts a bunch of little lines made up of triangles. If you have flat faces, we'll see a little bit later how you can actually approximate everything with a triangle. So where do they come from? Mainly, and where we work with, so we work with SolidWorks from TriMech, and that's where we generate our STL files from. We do our 3D CAD design there, but you could use Inventor or ProE or any of the other engineering software packages. These are your premium CAD engineering software packages. Then you have your free CAD software. You download these online. They don't have the same features as your premium CAD software. This is more for the maker community. So people who are using little maker bots or the low-end consumer-grade 3D printers, they're probably using some CAD packages like these. But you can also output STLs from digital animation and 3D sculpting software, like 3ds Max or Rhino, Maya. So these are things that they use for making cartoons and TV shows and movies or video games. So you can take what they've already drawn and just save it as an STL file so you can go 3D print it. And then lastly, you could use somebody else's STL files. So coming from services like Thingiverse, Instructables, GrabCAD, these are just all places where you can deposit your own STL files and then somebody else can go download them. So somebody else draws an action figure, you can go online, download it, and print it on your own machine. Again, that's something for the maker community, not really for industry. The other thing to keep in mind is a lot of these free software and free services are owned by 3D Systems, Stratasys, Autodesk, SolidWorks. So yes, they're free, but they all kind of have this industry backing because they want you to move into their more premium products. So let's look at STL geometry. First thing we have here on the left-hand side of the screen is just a simple box, okay? It's made up of 6 sides. Each side is a rectangle. You can approximate that rectangle with 12 triangles now, okay? So you have 2 triangles on either side. It's a perfect approximation. Every rectangle is made up of 2 triangles. Your STL file is the exact approximation of your 3D CAD data. But now if we go to something, what if it's round? Okay, there really are no straight sides. The top and the bottom are flat, but there's really no straight sides. So what do? Well, at very low resolution, if we look here, very, very low resolution, your CAD software won't actually let you do this, but if you were to try to output an STL file, you could get many visible facets. So we have 10 sides in this case around the outside, and we have 6 sides, a hexagon on the inside. If you were to 3D print from that STL file, you wouldn't be very happy with your print. You say, well, this isn't a round disk. This isn't the washer I wanted to make. This is some polygon that looks nothing like my actual CAD data. If we take a look at some of the file properties, you have about 64 faces that make up that geometry, and it's about 3.3 kilobytes of data. So now if we go to high resolution, so now you're increasing the number of facets, you're approximating all those curves with little tiny facets, so to the naked eye, you can't even tell that they're there. But now look at the effect on the number of faces. Over 1,000 faces, over 50 kilobytes of data. For a small part like this, that's not a big deal. Where you want to be operating is over on the right-hand side of the page. So you cannot tell that your part's geometry is any different from your CAD model. Okay, so what if we go to something that is, let me go back. What if we go to something that is very, very complicated? So this is a model of a Martian tripod that we did. It's about 6 inches tall. It's made up of 18 different pieces, and these were all laid out onto sprue frames, and they were injection molded. It's a model kit that you could buy for a game, like a fantasy game. So if you were to look at very low resolution STL files, so you're looking at about 180,000 faces here to make up those 18 parts, about 9 megabytes. Even at 9 megabytes, you're kind of on that verge of, can I email this file to somebody if I needed to? You know, that's kind of a, something you have to consider. But that's at the very lowest resolutions. Now we go to a higher resolution. Now you're at 4.2 million faces and 208 megabytes. There's no way you're emailing that. But you got to remember this is 18 different files. Again, you want to be operating over there on the right-hand side of the screen. So let's go through some things that you need to do in order to save an STL file. First thing is you have some geometry, some CAD geometry. We work a lot with plastics, so that's kind of what I'm going to focus on here, and that's what we're 3D printing with. So if you have any hardware shown, be it threaded inserts, pins, bearings, whatever it might be, if those are shown in your part, before you save an STL, you want to hide those, because you only want to print the plastic part, you don't want to print the metal part. You're going to install that later. Same thing goes for construction surfaces. So if you're using surfaces to help with your CAD layout, whether you took that surface from a 3D scan or you took that surface just as some construction geometry earlier on in your part, you want to make sure that you hide those too. Depending on the 3D printer and the software you're using to process these STL files, it might actually try to print that surface if it is showing. Now you don't need to delete these bodies, you just need to hide them so they're not visible. You can keep them there in your file, just hide them so they're not visible. All the CAD software will give you that option. You could show them after you save the STL file. And then from there, it's as simple as file save as STL. It's very, very simple to save an STL file. But the first time you save an STL file, you need to kind of set some parameters. Can everyone still hear me okay? Yeah, okay. So you go to File, Save As. The first thing you need to do is select the file type. Just like saving any other file format, you pick STL from the options. And then you're going to go down and you click the Options button. This is in SOLIDWORKS, again, the software that we use. It might be a little different for other CAD packages. So then this window pops up in SOLIDWORKS, and these are all the STL settings that you have to work with. First thing you're going to make sure you select is you pick a binary type STL file. The difference between binary and the ASCII, not really important for this, just understand the binary file size is much smaller. It's kind of a standard to use. And then you're going to go set these two metrics. The first one is the resolution, the first one is the deviation, second is the angle. To my knowledge, the deviation is actually part geometry dependent, so depending on how big your part is, that deviation will actually be different. So what we do at Creative Mechanisms is we set that at about 80% of that slider. So there's a slider there in SOLIDWORKS. You just move it over to about 80% of the maximum, and then you set the angle at 3 degrees. A few years ago, each one of the 3D printing machines would tell you where to set these. Now they just tell you to click Fine. So if we go and we see that option over to the left of that circle, you have a few different resolution options: coarse, fine, and custom. Right now we're on custom because we're setting them ourselves. They say you can just use fine. If you click fine, those sliders will actually move over to the left. You'll have a lower resolution. We find using these settings to be the best. The other thing you want to make sure that you don't click is this save all components of an assembly in a single file. So if we go back to that tripod that I had shown, that was 18 different parts. It was an assembly file. If I save that as an STL, it would just put all those bodies together as one STL. I want them as separate bodies so I can print, orient them, arrange them all on their own for reasons like optimal build, direction, minimizing support material. And then you're also more closely mimicking an injection molded part. So you have all these different parts that you need to assemble, and you understand how they assemble. And then you just click OK. Pretty simple. You only have to do that once. So you do that the first time you save an STL file, and that's it. Yeah?
Another good little tip, too, is if you click Find, write down the numbers, and then if you want to do the custom,
Yes, you can, yes. So and again, you might be able to confirm this, but I'm pretty sure those numbers will actually change depending on your part. As I was making this presentation, if you have different parts, if I had this tripod up, those numbers would be different. The angle doesn't change, but that, what was that number? Sorry. But the tolerance, that tolerance number does change. So like I said, what we found, 80%, 3 degrees seems to be the best. All right, so let's go through this first walkthrough. Again, we have this tripod model. It's 18 different parts. So we bring up the pointer here. No, there it goes. Okay, so we just go File, Save As. We select the STL file type. In this case, I have 18 different parts. I want to save them as separate STL files. So I'm just going to delete the file name and just put a little hyphen there. Otherwise, that's going to be a prefix on every single file it saves. So I just put a little hyphen prefix. It goes, it saves all 18 parts. I verify that it saved them. And then if we go, we bring up Windows Explorer here. You see those files are populating. And now I have every single STL file saved. Alternatively, I could go in and click on each one of those 18 different parts, open it, file save as STL, and do this process 18 times. That's a big time waste. Just do it one time from here. And now from there, we would take it into the 3D printing software. In the case of Stratasys, that's Insight and Control Center. So that'll be our next walkthrough. Anybody want to see that video again? No? Get it? Okay. Okay, so now here's a walkthrough completely from 3D CAD all the way up to 3D printing the part. So we'll run through that. So again, you always start off, File, Save as STL. Choose where you want to save it. Confirm the save. Then you bring up the Insight software. So this is from Stratasys. You're going to open that STL file, and then the first thing you want to do is orient it in the preferred growing position. So we don't want to grow it like that. We're going to put it down on its side. And then we click the Slice button. It slices it into different layers. We click the Support button. It adds the supports beneath that. And then you click the Toolpath button. It automatically generates the toolpaths. In this case, there's no reason to modify any of those toolpaths. It's a simple part. We go to Save. And then we go and we come to a Control Center and we insert that file. It's called a CMB file. There's our little part laying on our build platen. We can add copies. You could fill up that whole platen. You could put other parts on there. If this were the case of that tripod, you'd have 18 different parts on here. They would all fit. The nice thing about this is it tells you how much material you're going to use, it tells you how much support material you would use, and how long it's going to take to build. And actually, once you click that Build Job button, all those numbers will fall to be actually a little bit lower. Anybody need to see that again? No? Okay. So that's pretty much it for creating STL files, background of STL files. There's all of my information. Any questions? I think we're actually going to save questions for the end of our presentation here once Andrew talks about the Faro scanner. If you don't want to bring up a question here, we'll be at the TriMech table all day, so you can just come up and talk to me if you'd like. Thank you.
Okay, thank you. So, hi, I'm Andrew Toft. I work for Faro Technologies. I've known Chris for a year or so, although we both went to Virginia Tech, go Hokies. That's right. And we may have cooked or drank beers with one another, cooked back and forth between different restaurants that we worked at a decade or so ago when we were there. But here lately I've been working with Chris because we both touch a number of different industries with our companies. TriMech, of course, is in design and also in 3D printing and in file management systems as well. So you've got all these files and different types in different industries and different manufacturing centers being able to communicate with one another and keep revisions straight and everything. Our company, Faro, actually uses that capability both at our headquarters in Lake Mary, Florida, where we've been for 35 years, and in our office in Exton, Pennsylvania, here locally, where we manufacture 3 of our product lines. My company, Faro, and I'm sure I have slides here that I can show. There's a lot of different workflows too that I want to get to, but our companies, we're publicly traded. We've been around for 35 years, and we started out with, again, two guys in their dorm room essentially who had an idea and produced this articulated arm for checking joint rotation. All right, they were biomedical engineering students in Montreal, and they developed this encoder and arm technology to solve a specific goal for orthopedists. And pretty shortly after they launched that as a medical product, maybe it was somebody that they were actually working on at the time, but they got requests for positioning and measuring with this device in an industrial setting, and then from that really grew the company that we've got now. So we have 35 years of experience and probably 22 or 3,000 customers worldwide at this point. And what we do primarily is portable 3D measurement devices. So this Faro arm is a major component of that, but what essentially we're doing with it is 90% of the time at least, this laser scanning STL function isn't part of the conversation that we're having. We're taking and we're positioning and we're measuring the flatness of the table by making contact with the table in different points and fitting that flat geometry through there. So we see the deviation between a number of points across a plane. If we want to measure an inside diameter, for example, we take 3 or more points and that will geometrically fit the diameter in there. Hey, Andrew Stone, how are you? It's been about 8 or 9 years since we worked together. Back there, where I first had my taste of laser scanning and STL creation and 3D measurement was at a small company called Aegisound. And what they were doing there, they hired me right out of school. What they were doing there was actually doing those custom earplugs that our keynote speaker had up on the picture there with the custom built for everybody's ear canal earplugs. And I walk in and I see this Geomagic software with an automated function, and all they're doing was they took an audiologist, they took impressions of people's inner ears, and they turned that into an STL by taking that impression and laser scanning it, create an STL, and then we're able to then modify it. So scanning something, where I kind of step in here, scanning something and then being able to put out that nice even STL file it's not magic. It's not a magic wand that I can wave to make that object on the table be all of a sudden printable or manufacturable. There's some post-processing, and in years past, there's been a lot of post-processing needed in the software form and also in the understanding of how big or small those files should be based on the geometry that we've got. Long story short was you had to basically run trial and error or take a lot of time and some serious money for software to be able to convert what we could output and what the scanners could output, which is this point cloud, and turn that into something that's usable. Now, let me roll back to just the workflows that we're talking about here. Let's say we want to get to the end goal of we want to be able to 3D print on one of these printers using an STL file or going from a CAD file to do so. But what we have on the table is a hand-worked prototype, or we have a legacy part that we've got no 3D model for. Then Faro and our hardware come in are helping you guys decide, helping the industry decide how far they want to push their capture of that part. To a certain degree, these machined parts, these prismatic parts, are easily broken down to simple geometric levels. So you can take a look at, for example, this ball valve is a couple of cylinders that intersect one another. And there is a flat for the bottom and there's a flat for the top. And there's a certain diameter and a little bit of a cutout here. But what we're trying to accomplish with this may be simple enough that we can touch that geometry and just create it manually. So go ahead, I'm just going to quickly get to that workflow. We do a number of things we can talk about later, but here's the basics. This might be all I need. These flat components might be all I need in order to capture a part that's mostly prismatic or a machined part, and then export that through to SolidWorks, for example, to create and model that 3D model. And then it can be either broken down, just like Michael said, to a STL that can be printed, or it can be put on a CNC machine, right? So there's a number of things that can be done with that. But this capturing of the geometry, essentially what you get is, if you looked at it, I think I'm losing my video feed here. Hang on just a second, is that better? The cord's kind of on a lift here. Would be touching off on these features and you'd have something that essentially looked like that on your screen. All right, so that's kind of where we come in first, is breaking down the geometry, and then we export the geometry out of whatever inspection or capture software that we have, or right inside SolidWorks using one of the plug-in softwares. So you're sketching using the ARM, for example, and export it as a Parasolid file or as a IGES file, and pull that into then, in this case, a Parasolid file, open in SolidWorks, choose a Parasolid format, couple of settings, and this is what you've got. That's enough for a designer to trim together surfaces and punch through holes, and that might be all that someone needs. Very simple, it's not very expensive. The ARMs have been around for 35 years. Gantry CMMs have been hand tools, and keying in that information have been around for a while, but to a certain degree, we can take and look at something in reality and pull it into the digital world faster than keying those things in, faster than just clicking them and saying that, hey, I need a thickness to be an inch. This actually pulls it in as built. So there's your clear geometry back for a second, and your coordinate system in the middle of the part. And you extrude it and you have a solid model, okay? So this may be, if some of you are thinking like, hey, we got to get into 3D scan and we got to make 3D parts, turning them into STLs, we can skip this third-party point cloud idea completely if your parts can be broken down to a more simple level. So that's one interesting thing, is that you go directly into the SolidWorks software or Inventor software, or back to SolidWorks software again, and then export that either as an STL or as an IGES file or as a format that your 3D printing software or CNC software can cut. Where it gets really interesting is when that geometry gets more complicated. So what's a portable CMM? It's a relatively old piece of technology that's got a lot of development in it. It tracks where that probe is, and it also tracks where the laser scanner on the end of it is in space. What's 3D scanning and how does it work? We'll get there. And then the Ferro arm, which we can talk about offline, but it's one of many devices out there on the market that can capture data as far as laser scanning is concerned, and it's one of fewer that can capture both that hard data at a tight level of precision and the scanner data as well. So Ferro, they sent me this great file of things I should talk about, and we could really highlight the types of things that we do. But laser scanning has had its obstacles in the past as far as being able to digitize and capture geometry. On an arm, you get to work your way around a part, so the line of sight isn't the biggest obstacle. But what has been is the material type. So let's say we have a really dark part. We have a stealth part like that F-22 Raptor. We've got some pieces on there that were dark. We would have had to spray paint those or add something to them in order to be able to scan that in the past, right? If you've ever gotten parts back from somebody, has anybody used a 3D scanning service or 3D scan? If you've ever gotten parts back from somebody like that and they're kind of white powdery on the edges and stuff, they sprayed it with a fairly toxic stuff called Magnaflux Developer Spot Check. It's not good for you, and you don't even want to read the sheets on it. But the idea is you're trying to dull that surface. You're trying to make it more light colored, so that the light that you're emitting to measure something doesn't get absorbed. So dark materials were tough. Reflective materials wreaked havoc on what we were trying to do. Imagine shining a light on something that's a mirror polished chrome boat propeller was the first thing I scanned with this. And the light goes off in the room and the cat's chasing it across the couch. I say that because my wife and I both worked for Faro, and our cats go nuts every time they see us break out the Faro arm. My 2-year-old really likes it too. Long story there, short, is that reflection really wreaked havoc on the types of things that we could scan without having to coat them. When we get into medical products, when we get into pharmaceutical companies and trying to reverse engineer an impeller to pump purified water through a vat at Merck, I've got to think really hard about how I'm going to scan or collect that data so that we don't add anything to it, so that we don't contaminate a part. So here, the arm, essentially, you're emitting a laser, you're triangulating that laser and what surface it's on with the camera. And I just want to skip through because I think I'm running out of time. We laser scan, our scanner's fast, it captures data. The resolution of it's extraordinarily high. You can see every stitch in a piece of material, in a car seat, in an aircraft seat. You can see the height and measure the height of the ink on a foil stamped label. We can see the surface texture on the Konica Minolta camera there, a Nikon camera. That's a 1-inch tall statue, and you scan that and you probably have, when we're talking about file size, 4 million or 5 million points that translate into a relatively large file size. But what we're looking at is this point cloud is a bunch of individual points, and they all have an X, Y, and Z value and a vector by which they were returned to the camera. The way we create an STL file, or our software creates an STL file, is it's basically a one-click. You get an STL, depending on how many points you have, it's going to connect the dots, if you will, between nearby points to each other. And instead of defining a surface on a bunch of little points and where they kind of sit and where you could wrap a surface across, it's like scales. It's tiny little tessellated facets that define the surface. Where I laser scan somebody's fingerprints here, and you can see the gaps between their fingerprints, I'd have to have a really tight mesh, right? Really tight STL in order to see that resolution. And where it gets interesting, really interesting, is when you have really big and really ugly things to have to scan, like this guy right here. The character on the left is just a mannequin that was used at a design group, wrestler group downtown Philadelphia, and we were able to scan that and turn it into an STL. And because we had 40 million data points on it, we hit a button that looks like a filter, and it decimated the model. So instead of 40 million points, I allowed it to keep 10% of that. But there's a little slider in the software actually that allows you to choose whether you want an equal triangular mesh STL, or one that maintains higher density and smaller triangles in this case at the edges or at the areas of greatest curvature. So there's a little slider in between that you get to choose, and what you get is tighter, more dense data in areas where that changes a lot, and more sparsely populated mesh in areas where it doesn't. So it doesn't have that much of an effect on your geometry, but you can keep your file size a little bit smaller. All we did here on cleanup of the scan of Chris's face was actually just trimmed some of the boundaries and threw away 90% of the data and said I want to make a mesh of that. There was also a couple of little holes where like eyelashes and eyebrows got in the way, and it's at this point, at least in the software, it's a matter of clicking on that hole or saying every hole that's larger than whatever distance it is, and there's a slider for that too, it patches it. It looks at the geometry around it, and it either patches it flat or it patches it with a little bit of curvature to match what's around it, and it's up to you. So there's a lot of little check boxes for that within these softwares, but essentially we can superimpose these two things on here. I thickened that STL and made it printable. We could easily have printed a mold or a mask from that. The scan that we took there was about 10 seconds worth of scanning with the arm. So he's just stayed really still. I think we propped his head up against the wall behind and did a couple of spray paint passes across it, which was pretty interesting. Now, those are STLs. We're in traditional design and manufacturing of things. The old question would have been like, what can I do with that point cloud? Can I bring that point cloud in to SolidWorks? And the answer is no. It's so big, there's so many points in there that SolidWorks doesn't know what to do with it or can't compute that much. Now it's, what can I do with that STL? Well, you can do a lot with an STL. You can print it, right? If you optimize it, you can print it efficiently. You can scale it, you can thicken it, you can push and pull. They even have a little device where it's like a sculpting tool that gives you force feedback, and you can sculpt into that like you're a sculptor. There's a software that allows you to do that. You can do geometry for jewelry with it. What I did here was I made a mesh, and then I said, what I'd really like to have is an as-built document, but a solid model, a solid IGES file that we could then sketch on top of or build from within a SolidWorks program. And so it was not quite a one-button click, but it was pretty similar to a one-button click, in which I said, I'd like to auto-surface this. And the software now at this point reads the curvature change and develops 4- and 5-sided patches that basically define that surface. It wraps over top of all those little tessellated triangles to a certain degree of accuracy, a patch, and then it connects these patches so that you have another mesh framework. And it's a small enough mesh that you can bring it into SolidWorks as an IGES file. It's a relatively small file. And then you trim it on the bottom, and you wind up with a solid model. Now this model can be machined, right? So some CAM softwares can handle an STL for machining, right? CNC tool pass from an STL. Some softwares can't do that. And some modeling softwares can't then build on a framework. So if I was going to build a helmet, like my Gentex folks over there, from this, I would want to go, this anthropomorphic head is, the ideal or the golden size or the large or the small size of what we're trying to produce here. Or this is a custom helmet for a specific pilot or specific operator. And we're going to make this perfectly fit them and link in with their communications. There's options there, right? You can do any of those things now. But the idea is you have to get into a format that you can use it. When it comes down to a cast part, this wasn't the best example of a cast part for me to bring. It's just the only one that I had that wasn't terribly proprietary. There's not a lot of draft on this. This was an investment cast piece. There are some fillets that are fairly complex. But the idea is if I scan this, I would want to then pull geometry. If this was a legacy part and I was trying to make a finished CAD model or a parametric CAD model, which is one where you're not just scanning and taking for gospel that the thing you've scanned is exactly what you want to produce and replicate, right? You want to go, I need that scaled, I need that larger, I need that smaller, I need that sketch that we create this with to then be scalable, editable, able to be optimized using some of the software tools that we have available to us. I want to do flow analysis software. I don't want to investment cast that, I want to print it. I don't want to investment cast that, I want to sand cast that. I need 10,000 more than we can handle with the investment cast process right now. There may be a lot of factors that cause you to go, I don't want to make that out of steel, I want to make that out of aluminum, for whatever reason. Excuse me, guys, I'm suffering with some allergies here. Laser scan looks like that, okay? That was like a 5-second laser scan right there on the top left. But what you get is a capture of the surface, right? I'm reflecting that blue laser line off the surface. I'm taking 500,000 points a second to capture that. And what I get from it is an accurate to plus or minus 0.02 of an inch collection of data. That's a point cloud. Sorry, go ahead. 5 minutes. Okay. I thought you were telling me to stop. Good, I got 5. I'm almost done. The next step with this would be, okay, if I wanted to just print that as is, as cast, as found, I would have taken another 10 or 20 seconds to scan that from almost every angle, and I might even have used the probe on the arm to reach down inside the bore and measure its physical diameter and depth and counter bore from both the valve body entrance over here and the main bore. And then I would have gone, okay, I'm going to smooth that. I want to decimate that, right, the little filter tool, and I want to keep the areas of highest curvature, more dense than the others. And then so I take that from a 10 million point scan to a 2 million triangle mesh, and we send that to Chris, and he puts it into the printer, the Stratasys printer Insight software, right? And we go to it. Now, if what I want to do was give it to the engineering consultancy, right, or my engineers in-house and go, we got this legacy part, we have access to it, we have the IP for it, we're not trying to rip somebody's product off, right? We're not making counterfeits necessarily. Maybe we're analyzing some competitive products, because that gets done. But we're taking this part, and we want to use this part in this basic geometry because we've got a supply chain in place to make these types of parts very quickly. But we need it to be longer, wider, bigger throat, porter polish inside of it, whatever it might be. Here is where we take that mesh and we take it the next step when it comes down to the engineering level. We break that mesh automatically into a bunch of different colors. Those colors are all where the curvature starts to change. It picks out specific types of features because I want to pick those points, those data points that lie under there, and I want to fit, using metrology practices, I want to best fit or min or max fit geometry to them, and we can just go, okay, that top surface, that's a plane. That bottom surface, that's a plane. This front surface, that's a plane, just like we broke down our prismatic part probing it. And that little piece there, it's kind of an extrusion off of that part. So what we actually did was pulled, like this blue one on the bottom right, we pulled a sketch plane through the part based on the front plane of that little extruded piece, this little kind of house-shaped extruded piece. And we took that profile, then we took that profile and said extrude, so we extruded that in. Okay, this is within this Geomagic software. The next step was where the fillets are and how they sit and the tapers. Some of them were helical, or some of them rather were spherical. I actually cut a profile and created a sketch. Now, where this gets interesting is that sketch it's got a model tree, it's got history, so that sketch is constrained and that sketch is editable. And when we're done to the point where we've got that gray top right part showing, we've got a part that's been based off of accurate scan data. We've got a part that's got a couple of extrusions and base geometry and a revolution that's based on a sketch. That can then be live transferred out to your SolidWorks program. So SolidWorks opens up in the background as a second window, and the feature tree and the history tree start feeding in, including that sketch, right into your SolidWorks so that it builds in fast forward before your eyes. In some cases, and I've talked to some people who do this, in some cases you've got to slow down a couple of your steps, like trimming with freeform surfaces, one at a time instead of 10 at a time. But what you get is a part that then your engineering consultancy can take and edit and run through flow analysis software or run through an FEA practice of some sort, and then make a change to that sketch without having to completely rebuild the part. So maybe what we're looking at is this is where kind of the magic really happens, but you still need to have that intellectual capability. You still need to have that engineering understanding of your form fit function. It's not just an automatic copy machine. So and one last thing is, if it's going to be an automatic scan and a production of something in printing, it might be a worn out part that you get. You might not have one good known part, so you can add in the STL world a little bit, but you can do much more in the SolidWorks realm. So sorry, it felt like a whirlwind. There's a lot of things on my mind about this, but do you guys have any questions?
So we're going to have to wrap it up because it's a little bit past 3. But if you have a quick question, someone.
Chris, why don't you mention just real quick the training aspect of it? I mean, this was real high level stuff.
Sure.
People went
overhead. So why don't you-
So I just to, real quick, because Dale, we get started at 2:10. The idea with anything that you're doing with printing and with any high-level processes, garbage in, you'll have garbage out. The richer the data you have into your printer, the better the print you're going to have. So that's the idea. And same thing with the scan. You have to have you got to put the time in to make that the right decision. So a little bit about what we're doing with SolidWorks and NEPA, and even a lot of times, Faro is you have to train on these processes. With the Insight software, there's a whole week-long training class on how to get the most out of that software so your prints are quality. And we're partnering with NEPA, running SolidWorks training at their facility, at their training lab in NEPA. And any questions about, if you want to look more information about that, please contact me. I'm right outside the door here. We think 3 questions. I remember the keynote saying, you got to ask a question. So I'll count down to 5. If not, I'm going to pick someone.
Question on the scanner. Is
Right.
it just laser, or is it laser and touch?
It's laser and touch.
Laser and touch.
Yeah, absolutely.
And accuracy is about the same when you're getting both modes?
Yeah, so the touch is really where the arm scaffolding comes in. Plus or minus 1/1000th of an inch is a good benchmark. The laser is plus or minus 1/1000th of an inch, and so I just add those together. Right? It really can be a little bit less than that, but plus or minus 2. Longer arm, plus or minus 3, 3.5 if it's twice this volume. Yeah.
Question about this particular unit. This is a mobile scanner.
Right.
Okay. Is this considered a large one, a small one? And is it made for particular
Sure.
hospitals or
Yeah, this is relatively small, and I say that there are small units. So for the earplugs, we had a little, box-style scanner. You put the earplugs in, and it scanned, in a couple of different directions. This is a 9-foot working volume. I've used this in that we were talking about Cobra printing, 3D printing. I actually scanned an entire Cobra kit car from Backdraft about a month ago, 2 months ago, and you reach as far as you can, and then you hit some targets or rivets on the body, and then you move it. Then you hit those targets again, and you're back in your job. So that it allows you to increase volume a little bit, but there's much, much larger scanners out there. There's architectural scanners that spin around, in 2 minutes, and will have captured 100 million data points, color, and every one of you guys, everything that it could see. So maybe a shadow, and you might not have data points behind somebody, but you've got the walls, we've got the shape of everything, and you can do civil engineering projects with them. So one of those that we have does 330 meters on either side of itself at 1 million data points a second. So that's a big volume. The accuracy level of that's like a couple of millimeters at the near range, whereas this is more of like a small part, machine part, cast part, and tooling capable type of level of accuracy. So small on the general scale, large on the small part scale. Right.
Yes, sir.
So I know in 3D printing world, STL is the model file. I know that there's a lot of talk about introducing a new file format, AMS. There's different consortiums that are doing that. And that actually contains the virtual reality side of the file. So it's taking the texture, it's taking the colors, and incorporating that as well as the STL data into one unique file now for these newer printers that are printing
Sure.
colors. Does the scanning system capture that?
Yeah, our architectural scanner and our freestyle, it's a handheld scanner for the civil engineering and the historical preservation type of markets, does do that. It captures in color, and then that can be applied as well. This unit isn't designed to do that, but it would be fairly simple to make it happen. I've even been able to scan something and then in photogrammetry apply a picture to that for texture information and for color information. It's a great question, by the way.
Actually a break, so you have, anybody who has more questions can stay and just come right up to you, but you actually have a break till 3:30. We're just trying to keep everything on time to get you guys. Thank you.
Thank you, guys.